And so what we've looked at was looking at the alkene as a base, and then we addressed some of the potential nucleophiles that could follow that up. But there is another base. That other base, as we'll see here, is the alkyne. Okay, so could the alkyne act similarly as our alkene? Well, yeah, it has a pi bond. We've got strong acids, so why not? Couldn't it just go through and add a hydrogen and a bromine across that pi bond? Okay, well, potentially. So let's push this a little bit further. Let's attempt a mechanism. So the first step is that we share the electrons between our alkyne and our acid. The result would be that we would still have that pi bond because we didn't touch it. We've put that hydrogen on. We'll go ahead and show that as a red hydrogen, and then we'll show the black hydrogen that was already there, and then we would form, a carbocation. And that would be a carbocation on an sp2 atom, and that's not particularly stable. So if we were looking at an energy diagram here, we might be a reactant now going up to an intermediate to go all the way back down to a product. Okay, that very first step is going to be a bit of a challenge. Okay, so we might go through and say that's just not likely. Okay, but what if? Okay, so let's just say we did that. Right, we powered through, we built that system, and now what happens? Well, now our bromide could potentially come in, share, and now what do we get? Okay, well, now we would get that product. Okay, but what does that product also have? Well, it has a pi bond. Okay, the alkyne wasn't likely to react. The alkene actually reacts fairly swiftly with acids, which means we wouldn't stop here. Okay, this reaction would continue a second time. Okay, where should we place that new hydrogen? Well, it's going to go to the same spot. The rich get richer. We would have our bromine connected up here. Whoops. Let's call that our, no, we can call that our red bromine. Our red bromine, we have a carbocation. The blue bromide can now come in and attack. And we would end with a final product with two bromines connected to it. So if we could somehow do this, cool, it would go all the way through and we'd get the double addition. Okay, so it may not be super synthetically useful, but we can go through and do this. Okay, so if we push through and did this, we would end up forming that crazy unstable carbocation. So Markovnikov showed us this nicely, but then let's just say we could continue. Okay, so we can overcome this, it turns out. So what we can do is we just add a ton of HBr. Okay, so much so that the alkyne really has no choice but to interact. Okay, and we give it a bit of time. Okay, so we can overcome the obstacles of the very high energy sp2 carbocation that we said we weren't allowed to form before. We're allowed to do that if we just shovel crap at this and just kind of give it enough time to force through. Okay, one of the reasons why it helps us, or we can evaluate this, is that the product ends up being more stable than the reactant. And so by throwing a whole bunch of things at it and giving it that time, we can overcome those thermodynamic, or we can overcome those kinetic barriers to achieve our thermodynamic products. Okay, and so we end up forming, okay, so the slides aren't showing at all what I thought it was going to show. We would end up forming our geminal. Remember how we talked about that in the past, geminal versus vicinal, our geminal dihalide. So here it is. Geminal means the bromines are kept the same carbon. Okay, so we can go through and do that. So we really just have to throw stuff at it. Time is typically not written in your reaction, but you could see it as something like 24 hours. So you might see time listed there. But excess HBr, yes. Okay. this reaction in and of itself isn't as big of a deal. Okay, what we're more concerned about is, say, what if we use the other nucleophile? What if we used oxygen? Okay, would we expect this one to be high yielding? Why or why not? Okay, well, in this case, we might say it's going to be lower yielding, okay, because it's harder to get it initiated. We're still going to have that sp2 carbocation. It's not very stable. Bromide, at least before, the halogens were stronger nucleophiles, so once they were there, they could go on. Water's a much weaker nucleophile. It's going to be harder to get this thing to go through and react. Okay? But, why not? Let's just do it. Let's just say, slam it. We'll give it some H2SO4, we'll give it some H2O, and we'll just give it time and see what happens. And it turns out this reaction actually happens quite fast. But well, what the F? Why did it happen so fast? Don't we still form that incredibly unstable carbocation? Yes, we do. Okay, and that as an intermediate then reacts with our H2O. And so our H2O can now shuttle its electrons in. We would form our first, or one of our secondary intermediates, where our oxygen's connected. Again, the oxygen would now be positively charged. We're under acidic environment, so we can't have hydroxide. Okay, another water would come along, deprotonate. So you could show that water come in if you wanted to. And we would have the resulting intermediate of our first step, okay, with the OH connected. Of course, then we'd say, well, it has to continue on, and you'd be right, it does have to continue on. Okay, so what does it continue on to? That's for you to predict, so you could draw out what you think it continues on to. And now we'll release the information. It continues on, and we would get 2 bonds to an oxygen. Wait a second. What the heck just happened? Okay, shouldn't it have ended with the 2 alcohols? Shouldn't it have ended there? Okay, isn't that what should happen? We just do another electrophilic addition and we end up with the geminal dialcohol. Okay, why now all of a sudden we're saying that it does something different and weird and bizarre, and we've never seen that before? Like, that just doesn't make any sense. Okay, well, that purple functional group, if we want to try and come up with names here, would be a ketone. And that red structure directly above it, well, that's an alcohol and an alkene. Wait, didn't we talk about something about alkenes and alcohols being an enol, and there was a keto-enol tautomerization? Yeah, you remember all that from chapter 7? Yep, here it is. Okay, so here's where it comes back. This is of incredible importance, and this reaction actually ends with the ketone. This is an incredibly common reaction. It takes advantage of the keto-enol tautomerization, which is huge in second semester. It really just plays this kind of simple minor role here, almost as a trick question in first semester. But this is where it's appearing. Okay, so we need to be aware of this particular reaction. We're still following the same basic patterns that we follow with our alkenes. We're doing the standard addition of 1 oxygen, okay, and we'd have the enol. The instant we see the enol, we should be realizing that we should be going to the ketone from that information from chapter 7. Okay, what isn't really being revealed to you in this particular unit, as I try and clean up some space, is that structure, when it undergoes a second reaction, can indeed form this structure with the 2 OHs. That species is what is known as a hydrate. Okay, the hydrate is incredibly unstable and will revert to the ketone. Okay, very, very quickly. Why is the hydrate an important thing to kind of address? Well, if you've heard anything about acetals, that's why it's important. The hydrate is a direct relative of an acetal. And you might be, well, like, I still haven't heard anything about acetals. Go figure, acetals are second semester chemistry, so don't stress about it. But why would we even care about acetals? Well, acetals become important because of carbohydrates. Okay, why is that important? Well, a large percentage of you were concerned or potentially going into pre-health or pre-pharmacy systems, pre-biological systems. That is all carbohydrates. Carbohydrates are acetals. Acetals are hydrates. Hydrate chemistry ties to the ketone. So all of these chemistries are interrelated to each other, and depending on how your biochemistry class decides to teach it, they will address that interrelationship and conversion between your keto or aldehyde, because it can happen with aldehydes as well, because they both have that carbonyl, okay, without secondary things affecting them, okay, are all interrelated, and they're an incredibly important topic that should really be taught in first semester, because a lot of you are just going to skip second semester when that's where all the chemistry that you need for pre-health really comes into play, okay, which is kind of unfortunate, but that's where it is. So for this particular reaction, what do you need? Because you don't need any of that acetal fun gibberish. Really what you need to know is for sure what's going on right here. In that big purple box, you have to have that nailed down. On top of which, you would need the mechanism nailed down for that. So here we've just kind of simplified it, given it to you as Cardi would give it to you. It's the same steps that we've already gone through and done. Okay? I'm going to pause, maybe. I lied. I'm not going to pause because that reaction isn't summarized on our slides or on our sequence earlier on, because the sequence earlier on just showed alkenes. We now have our alkynes. So our alkynes react similarly. We get some little tweaks and differences, but for the most part, they're pretty much the same. Follow those patterns, and you should follow them to a proper end.